Today we'll be talking about some organic chemistry today, so let's head right into it. We have 4 topics we'll be discussing all right here, but let's just start with it. We have some of the basics, so we have that a hydrocarbon is a compound made out of carbon and hydrogen atoms only. We can sort of see that in the naming, hydrocarbon, hydrogen, carbon. So it's stuff that has only those atoms, nothing else. And alkanes are pretty much simple hydrocarbons with no functional group. Another type of hydrocarbon could be alkenes, alkynes. We'll talk about those a bit more later. We also have functional groups. These are specific groups of atoms in an organic compound that determine the characteristics of an atom, such as their chemical properties, if they're going to be reduced, oxidized, what further reactions they can initiate with, and also some of their physical properties, going to include the melting point, mass, etc. And also something that's important to know for these chapters is the molecular formula versus the empirical formula. The molecular formula is atoms in the molecule, just like flat out. For example, if we have 2 carbons and 8 hydrogens, that's what we would write. But the empirical formula is going to be the simplified ratio. For example, it's almost like simplifying refraction, where both these are divisible by 2, so we're just going to write C1H4. We see the empirical formula all the time with ionic compounds, but for these organic compounds, it's a lot more common to see the molecular. That way we know our main carbon chain and all that kind of stuff. And we also have 3 different kinds of compounds we're going to see in here. We have the straight-chained one, the branch, and the cyclic. The straight-chained are one that just go straight out. Branch have like extensions going off of them, and cyclic are the ones we see in hexagons or pentagons. We don't really talk about the cyclic compounds that much. So let's begin with our functional group store. I like to define these as looking at which one it has the most similar name and telling the difference between those. For this one I have alkanes versus alkenes. An alkane is generally a hydrocarbon compound that has only single chains between the carbons, while an alkene has double chains between the carbons. The difference in naming is going to be the alkane has ANE, while the alkene has ENE. And for example, we also need to indicate the double bond for the alkenes. For example, for methane, which is shown with the 2 carbons right there, we wouldn't have to say that because there's only one place where it could be. But if we have, for example, I believe it would be butene, which has 4 carbons, then we would have to indicate if it's between the first carbon and second carbon, or the second carbon and the third carbon. So we would do this as but2-ene, but1-ene, and stuff like that. We also have the alkynes, which we have the triple bond, but honestly, I don't see any practice questions on these. I don't see much discussion about these. Just know they generally exist, that it is possible for these carbons to have a triple bond with each other. Next, we have the ketone versus the aldehyde. So the way I remember a ketone is because it sort of sounds like a key tone. So I imagine a key, how it sort of sticks up. And in our functional groups, we have that a ketone is when the oxygen sticks out of a carbon pretty much, has a double bond with a carbon, and it's just sticking out there. We have acetone to butanone to pentanone, and we all see that they have the oxygen sticking right up. While on the other hand, an aldehyde also has that double bond oxygen, however, it's always at the end of a compound. A ketone is always in the middle, an aldehyde is always at one of the ends. For these ones, we see that we have the oxygen sticking right up, then we have a hydrogen to the right, well, it could be to the left as well. And the way I think about this is that the hydrogen is hiding the ketone almost, so that's the best way I can imagine it. So the ketone is just one sticking right up all by itself, and the aldehyde, maybe that hydrogen is giving some spin pair repulsion, and it's hiding that double bond oxygen group. And at the bottom we see that the ketone is when we have the double bond oxygen with our R group and our prime group. R just means we have a general group of atoms. It's not being very specific at all. While on the other hand, an aldehyde has to have a hydrogen on one of the sides in order to be an aldehyde. And the endings for this, a ketone has the ending of -one, and an aldehyde has an ending of -al. Then we have the carboxylic acid versus alcohol. Now hear me out. There's a lot of pictures to the left, but right now we're going to focus on the right. And alcohol is a functional group that has O and H attached to each other. We sometimes refer to this as a hydroxide, because that's one of the polyatomic ions that we know, but it's just O and H together. The way I remember this is because alcohol has O and H in it, so it's like OH just right there. This can occur at the ends or in the middle of the molecule, and has an ending of -al, so alcohol, it's like the OH. While carboxylic acid, it's a bit weird, it's a bit funky, but I know how to know this. So imagine that you're in this wine store, right? You're getting this wine, woo, good for you. So you've got this alcohol you're getting, okay? We're gonna come back to that. You're gonna put your alcohol in a box. because you're going to go driving. You don't want to drink and drive at the same time. That's very, very bad. I guess that's Jay's PSA for the day. So you pack up this box, you go to your car, and oh, you need your key to get into the car. So you take your key out, and you unlock the car, and you get in. So overall, you put the box in the car. We have a car box, right? We have an alcohol, and we have a key. We talked about earlier how the key is a ketone because it sticks right up like that. So if you combine a ketone and an alcohol in a molecule, you're going to get a carboxylic acid. That is the genuine and only way I know how to memorize this molecule. If there's other ways, let me know down in the comments below, but I think that's generally the most effective method for me. And also the ending for this is oic acid. We see ic acid in here, but we just need to add an O. And also this molecule can only happen at the ends because it requires that double bond O and the OH, which requires 3 bonds. Therefore, if it happens in the middle, that's going to be way too many bonds for the carbon. It's not going to be able to be supported, so it's only at the ends of a molecule. Maybe you can remember this as, like, once you're done shopping, at the end of it, you're going to go to your car. I don't know. That's the elaborate story I can remember. Then we have some functional groups that aren't really too similar, and I think they can be pretty easily pointed out. So we have halogenoalkanes, which are generally organic molecules that have a halogen in them. Halogens are our group 17, which include chlorine, bromine, iodine, etc. So we would have iodoethane, 1-chloropropane, etc. And that's just the general gist of it. It's when you have these halogens inside it, and also whenever you have 2 of it, you would have di. So we could have diiodo, for example. And we still have to indicate the number of this unless it is the only possibility, which sounds sort of weird until it gets priority when naming. So for example, in ethane, it can be attached to carbon 1 or 2, but because it gets priority naming, it's always going to be that carbon 1 technically, because it's at the end. For example, let's say with the propane example, chlorine can be attached to carbons 1, 2, or 3, but because 1 and 3 are at the ends, it's going to be assumed to be carbon 1 in order to get the least amount in naming, right? Let me know if you guys want a video specifically on naming, like really specific examples. I'll also attach a link to it in the description below that gives more specific practice, and I'm always willing to answer more questions down in the description. I'm just trying to give a general description, that way if you see this, you aren't super confused why there's a bromine next to our carbons. Because then we also have esters. These ones have a double bond oxygen and a singular oxygen at the same time. They're sort of weird, sort of funky, but once we get used to them, they're not too bad. There's no obvious naming for them, but it's going to be YL, and the second part is going to be O8. And if it's only single bonds between the carbons, it's going to be ANO8. For example, say the example in the top left, we have ethyl propanate because next to our single carbon, single oxygen, we have a 2-carbon chain, and 2 carbons is going to mean eth, so it's ethyl. Then for our ones that are attached to the double oxygen, we have 1, 2, 3 carbons, so it's going to be prop, so it's propanoate. That's how we do it. We do the single chain oxygen side, then the double chain side. For example, we see the one in the top right, I could say. And next to our single carbon, there's 1, 2, 3, so it's going to be propyl. Then we only see 1 carbon next to our double chain, so it's methanoate. See, esters aren't really too bad. They're pretty recognizable once you see them. The only other one that could be similar is ethers, I think they're called, but we don't really deal with them in this class, so that might be a next year thing maybe, but you don't have to worry about them. Esters is the one that has 2 oxygens in it at the same time, just in this double bond versus single bond way. This is the way I remembered ethers, but maybe you can use it for esters. It's sort of like you have oxygens on either side, or like ether side, you know, like you have 2 oxygens and they're both on like sort of different sides in a way. Then we have amines and nitriles. I'll be honest, we barely talk about these, so you don't really have to panic, you don't really have to worry. If you want to memorize some, memorize alcohols, memorize carboxylic acids, focus more on those completely. These ones, they don't really matter as much. So we have amines, which have NH2. That's their characteristic, it just has NH2 in it. Then nitriles, it has a cyanide in it, we call it, so it's like a C with that triple bond with has the N. And the endings are really simple. You add amine or you add nitrile. The naming isn't really too complex. That's just what it is. But absolutely, please focus more on the previous ones, telling the differences between those instead of these ones. These ones don't really come up as much. Alrighty, now we have our second section of the characteristic organic reactions. So we're going to start with some new vocabulary and go into some that's maybe more similar later on. We have a homologous series, which is pretty much a functional group in action. A functional group might be alcohol, but a homologous series is methanol, ethanol, etc. when we actually start like naming it. To be honest, you don't really have to worry about this definition. I don't think they'd flat out ask it. I asked my chemistry teacher for it. She didn't entirely know on just like in a second, so I don't think this definition is really as important. But then when we have a saturated compound versus an unsaturated compound. A saturated compound is when it has only single bonds and it's also solid at room temperature. Well, it's only characterized by having those single bonds. And a fun fact is that it's solid at room temperature. I remember it because it has an SSS. While if it's unsaturated, it's going to have a double bond in there, or maybe even triple bonds, and it's going to be liquid at room temperature. A good example of this, if you're good with biology, this was an example with lipids and how we have ones that are sort of like turned a little bit. Those turned ones are ones that are unsaturated. They don't have those straight lines with the saturated ones. Then we have our nucleophile and our electrophile. A nucleophile is what's most likely to give a pair of electrons, and electrophile is more likely to accept those pair of electrons. It comes back to how some atoms are more likely to donate an electron, some are more willing to receive. It's often based on their electronegativity, their likeliness to take in a pair of electrons. But yeah, I mean, it's not really a new idea for us in chemistry, but it's definitely a new word for us, and we're going to be using those words a lot. Then we have heterolytic fission, which is the breaking of a covalent bond in which one atom takes both electrons from the atom. We see a positive and a negative ion form. For example, if we have HCl, it was split into a positive hydrogen and a negative chlorine. This is what we see a lot of the time, and this is what we often assume in for some of our previous chemistry. But later on, we're going to talk about homolytic fission, which is definitely different and explores a lot of new concepts. Next, we have some of our just general reactions. We've been using maybe some of these words before. We have addition, which is the formation of a single product into from two or more reactants. So we have our ethene on the left, then we have the bromine, and when we add them together, we get, oh god, it's really hard to name because there's variations in naming this, and we'll talk about this in section 4. But we get two things added to equal the one thing. That's just general idea. Adding it, 2 plus 2 equals 4. So we're adding these two things to equal the one thing in the end. Then we have substitution, which is the replacement of one atom or a group of atoms by another. For example, we can get to points where maybe we replace an alcohol, an OH group, with a halogen. It's just like substitution is just taking those things and switching them out. That's it. Then we have elimination, which is when a small molecule is removed from an organic compound. It's like taking it out. We don't necessarily replace it with something else, it's just being taken out. Perhaps we take it out and then there's a double bond formed, so those carbons are satisfied with each other. We don't necessarily need something to move in, we're just subtracting something from it, and the molecule is just vibing now. That's sort of the idea versus substitution. Then we have hydrolysis, which is the breakdown of a compound by water. You can sort of think of this as if you have things that are like sticking together, maybe like you have bubble gum in the middle or something like that, you might take some water and like try to break it apart that way. It's like that, where we have this big thing, we add water, then it gets broken up into two different things. And we also have condensation, which is when two organic molecules join together and in the process eliminate a small molecule, H2O, or HCl for example. Condensation, if it's releasing water, that can often be called dehydration synthesis, where they're sort of being added together by eliminating that water. That's the exact opposite of hydrolysis. You don't necessarily need to know that, but it's just a little fun fact that this hydrolysis and condensation can be opposites of each other. Ooh, next we have free radicals. Free radicals are really cool, really fun, and I think they're amazing. So, a free radical is an atom with one, or sometimes more, unpaired electrons. Most atoms are really free radicals. We just never really called them this before because that's sort of a weird term to call it if we don't have anything to do with this information. But now we do. We can do a lot of things with them now. And the way we get free radicals is through homolytic fission. This is the breaking of a covalent bond where both the atoms take an electron. So This is when we have HCl turning to H with that electron and Cl with that electron. They're sort of a little funky, but we draw a little dot right next to them. We have the 3 steps of initiation, which is the input of energy to break the covalent bond. This is our homolytic fission step, where we're taking HCl, breaking them up into the 2 things. Then we have propagation, where the free radicals attack other reactants. And this goes on almost infinitely, so pretty much take this as there's a little angry toddler inside a preschool. And this little angry toddler is going to bug every single person. And the preschool is only going to be settled when everything is calm, right? And that's our termination step, where 2 free radicals, so these 2 angry toddlers, react together and form a molecule. You could almost, no, I won't say that. I was going to say, like, you can think of the reacting together as like the toddlers punching each other, therefore they're knocked out and there's no more chaos, but that implies the molecules just go away. So yeah, that metaphor doesn't exactly work, but that's almost what it's like, where this little toddler's upset, everyone sort of gets upset, some toddlers are chilled out, and then eventually the 2 toddlers remaining get chilled out, and they form another molecule. And now there's no more free radicals inside our reactions. So let's look at this example. We have A and B, which are bonded to each other, and with heat or light, aka we're just adding energy in general, we get A as a free radical and B as a free radical. That's the entire initiation step. Then we go to propagation, which is when, for example, maybe our A radical is going to go attack our happy C and D. Those 2 happy toddlers just chilling. A is going to come in. Maybe C helps calm A down, and now they're sort of happy with each other. But then D is now a radical, a free radical. So the free radical now is trying to attack E and F. So D and E are happy, but now radical F is really unhappy. So it's going to really continue on for a very long time, but also these atoms are really bouncing around, they're really small, they have a lot of energy, so they're going to be generally colliding a lot. So when we say a long time, we generally just means there could be like multiple reactions. It doesn't necessarily mean like it'd take a few hours. It really depends on the example overall. And then we have our final step of termination, where a free radical F is reacting with the free radical G, and they form Fg, and boom, they chillin', nothing's a free radical, we're all happy. And now we have our introduction into mechanisms. Mechanism sounds a little scary, but it's not, I promise. It's a step-by-step sequence of reactions where an overall chemical change occurs. This is an example, an example of this is free radical substitution, what we just talked about earlier, where we had a minimum of 3 reactions to get to where we are. There can be 4, 5, 6, etc., because propagation can occur for a not necessarily numbered amount of time. This is an example of a mechanism. It's a reaction where halogen atoms substitute hydrogen atoms and alkanes. That's what free radical substitution is, and that is where it involves initiation, propagation, and termination. Though we also have other mechanisms. We have electrophilic addition, where an electrophile, as we saw earlier, it was the electron pair acceptor. So it's things that is accepting these electrons, is going to attack an electron-rich area. It's almost like we steal from the rich to give to the poor. That's what it really wants. Or the rich are getting richer, I guess you could say. It really depends on which electrophile we're exactly dealing with. And the addition of this only gives one product only. So we're going to have two things that are reacting with each other, and they're only going to form one thing in the end. Honestly, you don't have to worry about these a lot right now, because later on in other chapters we're going to get very specific examples, very specific patterns as well, and it's going to make a lot more sense when we see all these things truly combining. And we also have a nucleophilic addition, where a nucleophile attacks the carbon atom in a carbonyl group, and there's addition across the C-double-O bond. And we also have nucleophilic substitution, where the nucleophile attacks a carbocation, which is a carbon with a positive charge because it lost another atom. This can be like a hydrogen, for example, lost it, and now it's a little too positive, wants to share one of those electrons. And this results in the replacement of an atom by carrying a partial negative charge by the nucleophile. Oh, I did not realize I had examples. Thank you, Past Jade. Okay, so electrophilic addition, where the electrophile attacks the electron-rich area. For example, this double bond that we see is going to be very rich with electrons. A single bond is going to be sharing 2 electrons. A double bond shares 4. This X is going to see it and go, ooh, that looks really nice. So they're going to steal some of these electrons. And also in the process, the sharing of electrons is going to cause the X to get bonded with that one carbon on the left. But we have a carbocation on the right that we still have, which isn't really super good, right? So we're going to have our Y come in, and that's going to take in that carbocation spot. So now we have two extra things bonded to this previous alkene. Next we have nucleophilic addition, which is where a nucleophile attacks a carbon atom in a carbonyl group and addition across a COO bond. So what's going to happen is that this double bond is going to give its electrons a little bit to that oxygen and make it a little bit more slightly negative. And this nucleophilic item is going to come in the middle because there's more electrons given to oxygen, therefore that nucleophile can really come in there. So it's going to get bonded, and then we see that this oxygen up there is a little too negative, so it's going to wish like, oh, I wish I had something positive sort of cancel me out. Hydrogen sort of strolling on by, O is going, ooh, you look nice, so they hook up together. So we have this new alcohol that is formed essentially with our O and then the H attached to that. Then we have our nucleophilic substitution where the nucleophile attacks a carbocation. So we have this exchange in electrons on the right where the bromine is getting some of the electrons and the carbon is just being a little more positive because of that. This hydroxide is a little negative, so it decides to hop in there and it just replaces this. We have our, if I was to name this, it would be ethanol. That's what it would be named. We have ethanol, and then bromine sort of tossed to the side there. So that's the end of our mechanisms that we're going to talk about for now, but we're going to get to a lot of more specific examples later on in other chapters. Now we have our shapes of organic molecules with pi and sigma bonds. Alright, so we have a bit of a refresher to start us off. So sigma bonds form when two atomic orbitals overlap end to end. We typically only talk about this with S and P. This can occur with D, but the syllabus is not covered at all, so we're only going to talk about S and P. When we have two S atomic orbitals overlap, we form a bit of like almost like a cow nose. Then we have a P and an S. We get this like almost like a bigger fish swimming to the right. That's the way I remember it. And then we have the two P's overlapping, which almost forms like a little sausage in the end. And it's also important to note, you don't need to really know why, but you need to absolutely know that a sigma bond is a single bond, and a double bond is a sigma bond plus a pi bond. So in our cyclopropane, we have nine single bonds overall, so we have 9 sigma bonds. You will, not you will, but there is a high probability of you getting questions asking for single bonds, to count sigma bonds or stuff like that. So it's important to know how to count these. Essentially, you just have the bonds there, and you count how many are single, and boom, that's a sigma. But also, when we have a double bond, we switch from not just like 2 sigmas, but a sigma and a pi. The way I think about this is like the recent, like I don't want to say like social media trend of like sigma males. These sigma males probably do not like each other. They're all like, no, I'm taking the red pill. No, I'm taking the red pill. So these sigmas aren't going to want to be super close buddy-buddy. So the propene that we have the double bond is going to be 1 sigma and 1 pi. I don't know what the pi really resembles here, but it's just the lack of another like sigma male who is intimidating the other sigma male. That's the way I remember it. That a double bond is going to be a sigma, then a pi, and then a triple bond is going to be sigma, and then 2 pi's. So our single bond is going to be a sigma, anything else we're just going to add on another pi essentially. So then we got to talk about hybridization, which is a really weird concept. It almost contradicts what we had before, but not really too badly. When we have an s orbital with 3 p orbitals, we get an sp3. When we get an s with 2 p's, we get an sp2. When we get an s orbital and 1 p orbital, we get an sp. It's sort of a weird thought, but I think it makes it better sense when we have some examples. So, for example, if we have beryllium at the top combined with 2 hydrogens, we have a sigma then a sigma, but we don't like saying that there's 2 sigmas. So we're going to say sigma pi or sp, right? Then we have our next example. We have a boron with 3 heliums. That's 3 sigma bonds. We have 3 single bonds, so that's going to be 3 sigmas. So we have, well, we don't like all those sigmas with each other. They don't like each other, so we're going to have sigma pi pi. So it's going to be sp2. So then when we have our methane right there, we have 4 bonds. That's going to be 4 sigmas. So it's s pi pi pi, sp3. It sort of makes sense when you look at it, but it's a really weird thought to start out with. We then have our nitrogen that has our 3 hydrogens, then the lone pair. So as a sigma, then pi, pi, pi. Our lone pair does count in this case. Well, I think, like in all cases. So we have sp3, and then our bottom one is also going to be sp3. So, knowing this, we can infer what the bond angles of these atoms are going to be, or general like sp atoms or general sp2 atoms. So, for sp atoms, they're going to be linear. They have a bond angle of 180. For sp2 atoms, they're going to be trigonal planar with a bond angle of 120. If you're confused about this, this was talked about in the Vesper, which is, oh god, valence shell electron pair repulsion. It's like the ones where we like talk about atoms in a 3D space and all that kind of stuff. How spin pair repulsion is going to affect all of them. Then we have our trigonal pyramidal, which is 109.5 degrees for each angle. And we see that trend generally continues because we have the same ideas almost. So yeah, SP is linear, SP2 is trigonal planar, SP3 is trigonal pyramidal. And now we're going to talk about isomerism, which is a structural and stereoisomerism, two kinds of isomers. When I said earlier in the presentation that I was trying to name an atom, but I didn't really know how to name it yet, this is what I was talking about, where there can be multiple ways to name one molecule, and we'll see what that means later on. So we have structural isomerism. This is when compounds with the same molecular formula have different structural formula. So we have three kinds. We have position, that changes the location of the functional group. Let's say I give you C3H6, would that be 6? No, it wouldn't be. Hold on, I'm going to type this out, then we'll make a lot more sense. Alright, I just typed all of them out. So we have C3H7Cl. So there isn't necessarily one way to write this out. We can put chlorine in the front or in the middle. And by doing this, we're going to have two different named compounds. We're going to have one chloropropane and two chloropropane. This isn't going to change many of the chemical properties because we still have a halogen and it's still a 3-carbon atom. But it's important to acknowledge this, that we can have different isomers that form. And you absolutely can get a question on the test that asks you, hey, write all the different isomers for this atom. And position isomers are one of the nice ones. You just sort of, you move the atom a little bit, then it gets named slightly differently. And in general, the main important thing about isomers is you always get a different name. For example, I can't have 3-chloropropane because at 3, well, if chlorine gets prioritization, it's going to be a 1 pretty much, right? Because we only have 3 carbons. So it'd be named as 1 instead of the 3. So that's an important thing to keep in mind, that you have to still follow naming rules, that the things will still get prioritization. Then we have chain, which is a little weird, but a little okay, where we're changing the main carbon chain. We can have hexane beginning with C6H14, and then we can take one of these carbons and attach it maybe on the second carbon. So we have 2-methylpentane. Then maybe we can get 3-methylpentane. We can't do 4-methylpentane because that would make it 2-methyl, because if you think about it, if we count from the right on the 2-methyl example, we have 1, 2, 3, 4. So 2-methyl and 4-methyl would be the same, but we name it 2-methyl because we like it when we have small little numbers. Small little numbers are easier to think about. We also have the other example of 2,3-dimethylbutane, where we have 4 carbons in our main chain, then we have 2 and 3. Then we have another butane example where both of our chains go off of the 2. So we have 2,2-dimethyl, like that. Chain isn't too bad, but it's easier to miss a few marks on that, so maybe give that a little bit of practice. Then we have functional, which is we're actually changing the functional group. I think this is truly the most common and the most realistic, that you have functional isomers when you have an oxygen somewhere in there. Because think about functional isomers, there's alcohol, there's ketones, there's aldehydes, there's carboxylic acid, there's a lot of esters. So many of them involve oxygen. And for this example, we have C3H6O, which can be propanol or propanone. Either way, you still have the same amount, and I encourage you to count all the carbons, count all the hydrogens, and see how it works in the same way. This is why it is not necessarily most valuable when they give us a molecular formula, because we can still name it in 2 different ways. We don't necessarily know what they actually give us, unless they say so in the question. And then, we also have stereoisomerism, which are compounds whose molecules have the same atoms bonded to each other, but different arrangements in a 3D space. For example, they might pretty much give us a name of a molecule, but we can still have variations when we draw it out. With geometrical, we have I think it's most commonly, if not always, it is when we have a C double bond, right? Because a single bond will allow atoms to move really freely. They'll just like hop around because the CC is cool. But when we have that double bond, it also has a pi bond that's going to limit the rotation. Because remember, a double bond is a sigma plus a pi. Pi is a little key strict because, well, not because. So that's going to limit how we can arrange the atoms. When we draw our structural formulas up here, it's sort of implied that these atoms can sort of jiggle wherever they like. You know, atoms are not super duper rigid, they constantly engage in reactions, etc. But with these, the double bond has a lot more energy in it, so it's going to be more firm with it. So with these isomers, we're going to have cis and trans, which cis means the same side, and trans means across. For example, when we have butene, we can have it so the butenes are on the same side as each other on the top, that's going to be cis, and when they're diagonal from each other, that's going to be trans, or when it's like top and bottom, that's going to be trans. A way you could think about this as like a transport is when you just get to one place to a different place. So you think like, oh, this maybe they go from here to here. That would be trans when it goes across the double bond. And I want to say the reason why these are isomers is, okay, so if we had two on the top or two on the bottom, we could just sort of flip it and boom, it'd be the same one. But if they're diagonal, we can never exactly move it to get it to perfectly overlap. That's why these are isomers, because they can be named differently because they clearly are different, right? They're not just rotated slightly. And we also have these optical isomers, which are when most of it's the same, but two are just slightly different. So the actual definition is if a carbon atom is bonded to four different atoms or groups of atoms, there's going to be two optical isomers for that. And these isomers are called enantiomers. I don't know how to say that word exactly, but essentially you can have multiple of these in an atom. We'll look at that a bit later. But if we have a CH2, CH3 at the top and an OH at the bottom, we can have two cases where H is on the left or it's on the right. And we can have the CH on the left or we can have it on the right. Either way, if I'm holding these two atoms, I can't exactly get them to rotate because I'm holding the atom with the one on top and with the one on the bottom. It's going to be a little weird because they will never exactly overlap. Then we have our specific chiral center, which is when a carbon atom with four different atoms or groups of atoms are attached. Pretty much this is why optical isomers exist. At the chiral center, that is where the optical isomer is going to originate, I want to say. So for example, in this, the optical isomer is that C right there, just a C that's only by itself. That is the chiral center for this overall isomer. If you think about it, that sort of makes sense because it is the center of the molecule, yeah? So for this thingy, we have two chiral centers in this. We have the one in red and the one in blue. I think skeletal formulas sort of make this confusing when we look at these, so I'm going to look at what's on the right. We need to keep in mind that it has four different atoms. So when we see the red carbon, we see it is attached to a hydrogen, a carbon, an alcohol group, an OH, and also another carbon. But the reason why these carbons are different is because one has that double O bond and that H attached to it, but one has the alcohol and the H attached to it. So because of this, they're going to be considered different atoms overall, right? Then we have with the blue chiral center, we have it attached to the OH, a C, an H, and a C. But the reason why these two C's differ, one is CH and one is CH2. It's a little weird to think about, but I think it's overall not too bad of a concept. For example, see the C on the far left, that has a hydrogen, then it has a double bond with oxygen. Because it has a double bond with oxygen, it cannot qualify as a chiral center because it has two bonds with the oxygen, therefore it cannot have four unique bonds. It can have a max of 3 unique bonds, and in this case it does. Then we see the one on the way right, the carbon on the way right. We have two hydrogens attached to it, therefore it's not going to be a chiral center because it has two of the same kinds of bonds, in which if carbon can only have a max of 4, every single bond has to be unique for it to be a chiral center. So this is also where we're going to be able to identify where our isomers are from this, because each enantiomers have 2 isomers. We have 1, 2, so we're going to have 4 isomers overall of this molecule. That's not the That's not all of the isomers technically, because those are only the optical isomers. We have to keep that in mind that while we have this, if they only gave us the molecular formula, then we can also apply our structural isomers as well. Maybe we can even, there's no double bonds, C double bonds in here, but if there were, then we can maybe apply some geometrical. See, there's a lot of room for these. So if they, for example, they could give you like a 5-mark question and ask you just point out the isomers, and boom, that could be an easy 5 marks for you. It really depends on what exam you get. But thank you for watching. I know organic chemistry is hard. I hope I made it a little bit simpler maybe. And if you have any questions, let me know down below. Thank you. Bye bye.